Today we will discuss one of the important spectroscopic tool in the pharmaceutical analysis, that is NMR spectroscopy, in a easy way. We have so many types of spectroscopic techniques like a UV visible spectroscopy, IR spectroscopy, fluorescence spectroscopy, but NMR spectroscopy is one of a special technique where we are going to study the nuclei and we will assess the nature of the structure. So in this video, let us see how easily we can understand NMR spectroscopy and what are the principles behind this spectroscopic technique. What is NMR? NMR is the nuclear magnetic resonance. So in presence of a external magnetic field, a nuclei can have the different orientations, and what is the effect of this magnetic field on the nuclei is going to be studied in the NMR spectroscopy. So in presence of a magnetic field, the nuclei can exist in the two states. One can be considered as a ground state and another one can be considered as a excited state. And when we supply the sufficient energy, the nuclei in the ground state can jump to the excited state, resulting in the absorption in the spectroscopy. So let us see a simple example here. So let us take simple example ethane. What are the nuclei present in this ethane? We can observe here two carbons which are equivalent. That means they are attached in a similar way. And it is also having another nuclei hydrogen. So again here all the hydrogens are equivalent because they are similarly attached. So ethane is having the two carbons and 6 hydrogens. These hydrogens can also be called as protons. So it is having the 2 carbons and 6 protons. But interestingly, here the carbon cannot give the NMR signal. On the other hand, here the proton can give the NMR signal. So within the ethane molecule, two types of nuclei are there. One is the carbon and another is a proton, but proton can only give the NMR signal. The reason is the carbon, which is the 6C12, is having the spin quantum number I is equal to 0, whereas the proton, which is 1H1, is having the spin quantum number I is equal to half. So in the NMR, the nuclei with I is equal to half can give the NMR signal. So now if we take the ethane is having the 6 equivalent protons. Since all the protons are equivalent, they will give a single peak in the NMR spectroscopy. But here the proton can give the NMR signal when we apply the magnetic field externally. So when there is no external magnetic field, the nuclei will not have any spin. But when we apply a magnetic field under the influence of this externally applied magnetic field, the nuclei can have the two spin states. The spin state with the low energy can be considered as a ground state, and another spin state with the higher energy can be considered as an excited state. So under the applied magnetic field, nuclei can exist in the either ground state or in the excited state. And when we supply the energy in the form of electromagnetic radiation, this electromagnetic radiation will promote the nuclei from the ground state to the excited state, which is observed as a signal in the NMR spectroscopy. So NMR spectroscopy is a simply one type of absorption spectroscopy observed by the nuclei having spin quantum number I is equal to half. This situation can be simply illustrated by a common example. Suppose a person is working in a company 1, and until unless there is no new offers, the person goes on working in the company 1. And at one time, suppose a new company is going to be established, which is a big company compared to the company 1, and they have given an offer to the person. Now the person can jump to the company 2. In order to shift off the person from the company 1 to the company 2, there should be some advantage. Suppose either salary is increased or designation is increased, there is a chance of shifting of the person from the first company to the second company. So now that we can compare the situation to the NMR spectroscopy. The new offer offered by the big company is nothing but the magnetic field we are applying, and hike in the salary is nothing but the energy we are giving in the form of electromagnetic radiation. So when we apply the magnetic field, the nuclei will have the two chances like ground state and exit state, but it can jump from the ground state to the exit state when we supply the sufficient electromagnetic radiation which resonates with the energy gap between these two states. So that is the NMR, nuclear magnetic resonance. Now what are the criteria required for the NMR signal? Just we have seen that nuclei should have a spin quantum number I is equal to half, and we should apply external magnetic field, and under this influence only the nuclei can have the two spin states. And then we have to supply the sufficient energy in the form of electromagnetic radiation that resonates with the energy gap. For most of the nuclei, the energy gap resonates with the radio waves, so we can supply the radio waves as the electromagnetic radiation in order to observe the NMR signal. But here we can have a doubt that why the spin quantum number of the nuclei I should be equal to half in order to show the NMR signal. Now let us see what is the reason for a nuclei to have I is equal to half in order to show the NMR signal. Before going to discuss why I should be half, let us see what are the nuclei which have the I is equal to half and can give the NMR signal. So nucleus is composed of the two important components, protons and neutrons. The spin quantum number I value is maybe either integer or non-integer, and it may have the any values like the 0, half, 1, 3 by 2 and so on. Even we cannot assign the I value just by seeing the particular atom. Still we can have a logic in order to remember which type of nuclei can have the I value as half, as 0, as 1. Suppose an atom is having the even number of protons and even number of neutrons, then I value will be 0. So examples include the 6C12. Already we have seen that carbon cannot give the NMR signal because the I value is 0. Now the carbon is having the 6 protons and 6 neutrons. Because the number of protons and number of neutrons are even, it will have the I value as 0 and it cannot give the NMR signal. Similarly, another example is the 8O16. The oxygen again having the 8 number of protons and 8 number of neutrons, both are being even. And similarly, the nuclei which are having both number of protons and number of neutrons as odd will have the I value equal to 1. Again, the examples include 7 and 14. So nitrogen is having the 7 number of protons and 7 number of neutrons, being both are odd, the I value will be equal to 1. Now if a nuclei is having one of the component as odd and another component as even, for example it is having the odd number of protons and even number of neutrons, or even number of protons and odd number of neutrons, then I value will be either 1 by 2, 3 by 2, 5 by 2 and so on. So here all such type of nuclei cannot give the NMR signal, because we have seen that for a nuclei to show NMR signal I should be equal to half. So among these nuclei we can remember those nuclei which are having I is equal to half, so that they can give the NMR signal. Now the nuclei which are having I is equal to half include 1H1. Simply we call the proton. So 1H1 is having 1 proton and 0 neutrons. Similarly 6C13, isotope of the carbon 6C13 is having 6 protons and 7 neutrons. That means it is having the even number of protons and odd number of neutrons. And another nuclei is the 9F19. So fluorine is having the 9 number of protons and 10 number of neutrons. So it is having the odd number of protons and even number of neutrons. Similarly 15P31, it is also having the 15 number of protons and 16 number of neutrons. So these are the examples of the nuclei which are having either odd number of protons and even number of neutrons, or even number of protons and odd number of neutrons. So these nuclei can have the I is equal to half, and these nuclei can give the NMR signal. Here we should not confuse that every nuclei with one is odd and another is even will have the I is equal to half. Because when one is odd and another is even, they may have I value as either half, 3 by 2, 5 by 2 and so on. And among these, only these nuclei can only have the I is equal to half and can give the NMR signal. So 1H1 we call the proton NMR, and 6C13 we call the carbon NMR spectroscopy. I is nothing but the spin quantum number. In order to see why I should be half, we can define another parameter, magnetic moment number. The magnetic moment number indicates the number of the spin states of a nuclei in the externally applied magnetic field, where m is given as 2 into I plus 1, where I is the spin quantum number. Now let us take a case 1 where I is equal to 0. When I is equal to 0, what will be the m value, the magnetic moment number? So m is equal to 2 into I plus 1, that is nothing but 2 into 0 plus 1, so which gives 1. So when I is equal to 0, m is equal to 1. That means the nuclei will have only one state, and this state of the nuclei will have a spin quantum number as 0. And let us take case 2 where I is equal to half, and then m is equal to 2 into half plus 1, so it gives 2. So now the nuclei under the applied magnetic field, it can have the two spin states, and each spin state will have a spin quantum with minus half as well as plus half. Now let us take the case 3 where I is equal to 1. So when I is equal to 1, m is equal to 2 into 1 plus 1, that is equal to 3. Now the nuclei can have 3 spin states under the applied magnetic field. These spin states can have an spin quantum numbers as minus 1, 0 and plus 1. Now let us see why I should be half in order to show the NMR signal. Now let us see the case 1, case 2, case 3. In the case 1, we have seen that I is equal to 0 and therefore it will have only one spin state and the spin of the spin state is 0. And in the case 2, I is equal to half and m is equal to 2. So now it will have the two spin states, and one of the spin state is of the plus half and another spin state is of the minus half. So plus half indicates the ground state and minus half indicates the excited state. Now in this case we can see that both of the spin states are equivalent, just differ in their sign. So these are having the similar magnitude but opposite signs. So such type of nuclei are perfectly suitable for the NMR spectroscopy. Now let us take the case 3 where I is equal to 1, then m is equal to 3. Now nuclei can have 3 spin states. I is equal to plus 1, I is equal to 0 and I is equal to minus 1. And here we can observe that all these spin states are not equivalent. So we can see that plus 1 is having some spin but 0 is not having any spin. So these spin states are not equivalent, they are not suitable for the NMR spectroscopy. Here the distribution of the spin is not uniform, so we cannot observe a perfect NMR signal in the case 3. So now the nuclei under the case 1 where the I value is equal to 0 cannot give the NMR signal. Similarly, the nuclei coming under the case 3 again cannot give the NMR signal. So nuclei which are having I is equal to half can give the NMR signal.